For this video, we're going to start talking about the natural history of California. And this is going to take us through several steps, including a variety of physical factors and how air moves and changes, looking at both the global scale and then kind of honing that into our local region. So we're going to talk about some geography, some geology, we're going to talk about rain shadows and atmospheric circulation patterns, and a little bit of the changes to the region. Now, since this class is focused mostly on California, we need to understand kind of the parameters of California and how that's going to influence the environmental factors around us. So we don't know where the mountains are, what built the mountains, where the valleys are, and where does water drain. So if we look at a California topography map here, all those. So here's the California topography map. The darker red the color is, the higher it is, the higher up it is, until it gets to these like lighter whites up there. And the greener it is, the lower the elevation is. So if you look at California, let it load back up. You can see that we have a red ring around California. In the middle, we have the valley. We have over here on the east side the Sierra Nevadas. Then we have Northern California up here, which is a lot of forest. Then we have the coast ranges, and then we have the transverse range that separates the valley from LA. And then a variety of mountains down in SoCal as well. What that basically means is that we are kind of in a big bowl here in the Central Valley, and that we are surrounded by mountains on basically all sides. And those mountains are going to do some very important things to the air as it moves through our region. Now, if we look at the fault lines, it's why we have mountains where we do. Fault lines are areas where the tectonic plates of the Earth come together, and there's different ones. Sometimes they will come together and push up and create mountains. Sometimes one will subduct under the other, and sometimes they'll split past each other. Now, if you look, here are all the fault lines, and if you look, the fault lines basically mirror the mountains. That's because the faults, the tectonic plates are what's building the mountains around it. So we're a very geologically active state. We have the San Andreas Fault over here. We have the faults that built up the Sierra Nevada mountains, and a variety of faults around LA. And so you can see that the fault lines really do map out what our underlying geography looks like. Now, we also need to understand where California sits on the global scale. So California sits roughly between 32 and 40 degrees latitude. Now, if you're not familiar with what latitude is, I'll pull up a map here. Okay. Now, here's California on the global scale. These vertical lines here are longitude lines. They separate the Earth in a circle all the way around. But what we really care about here are these horizontal lines. They're the latitude lines. And they go from the equator, which is 0, and then they move up. You can see they're increasing until they get to the poles where they're at 90. So 90 degrees north, and then they go all the way down to the South Pole at 90 degrees south. Now, if we zoom into California, here's like the California border here, I'm not sure what that yellow line is there. California border here, which is roughly around 42 degrees. But right about 42 degrees is where California and Oregon separate. And if we go down to the south, load in here, we have 32.3 degrees here, just inside of Mexico. And so we're just above 32 degrees. So from about 32 to 42 degrees covers the latitudinal range of California. So about 10 degrees of vertical stretch there that California moves to in the latitudes there. Now, that's going to become really important when we talk about how air moves across the globe. We're going to be talking a lot about 30 degrees and about 30 and 60 degrees. So you have 30 degrees south and north, and then you have 60 degrees. And those numbers are going to become very important for where air rises and falls. And so keep that in mind. California sits between 32 and 42 degrees. And that Fresno here sits right about 36.5 degrees or so. Okay, so here's the pattern of global atmospheric circulation. And so the goal here is to try and describe where plants are thriving, what type of plants are generated at different parts of the globe, and what describes California's environmental parameters here. What describes our temperature, our precipitation patterns, when it's hot and when it's cold. And to do that, we need to look at the global scale. And so we're going to look at the global patterns and slowly hone in on the local region. So here's the Earth, and you can see these latitude lines. So 90 degrees, 60, 30, 0, 30, 60, and 90 at the poles there. Now, we're going to be talking a lot about air movement and what happens when air moves. So if you take a big wildfire or something like that, that air that is being emitted by the fire, that smoke, it's going to rise. But why does it rise? Think about that for a second. Why does that air from that fire, why does it go up? Well, it goes up because it's hot. Hot air will rise, right? So it'd be really unfortunate if it didn't rise, because that means all the smoke would settle down and we would all basically be suffocated. So hot air rises, and if you look over here, here's some dry ice that's emitting some gases from it, and you can see that the cold air, dry ice is being very cold, as it's emitted, actually fills up the cup and then sinks down to the bottom. So cold air sinks, hot air rises. Now that basic pattern is going to describe most of what happens here on the global scale. So we're going to start here at 0 degrees. The reason why we're going to start at 0 degrees is because that's the part that gets the most sunshine. So if we go back to our map, if I can find it here. Here's California, right? Here's 0 degrees. Here's the Tropic of Cancer, and here's the Tropic of Capricorn. Now, those describe the northern and southern extent of where the sun will be directly above. So the sun throughout the year is going to basically move up and down. The sun's not really moving, but the earth is tilting back and forth, right? And so as the earth tilts towards the sun, the northern hemisphere tilts towards the sun, that's taking us into summer. So if here's the sun, as the earth tilts towards it, the northern hemisphere becomes summer, southern becomes winter, and as it tilts away, the southern hemisphere becomes summer and the northern hemisphere becomes winter. And so basically, the Tropic of Cancer, when we tilt it forward, the highest vertical point where the sun will be perpendicular to the earth is the Tropic of Cancer. And when it goes winter for us and summer in the southern hemisphere, the lowest point at which the sun will be perpendicular to the earth is the Tropic of Capricorn. So the sun basically, in a sense, bounces between the Tropic of Cancer and Capricorn and back each year. So let's say we look at the summer equinox. We have right here, we're going to be at the Tropic of Cancer, right? So that's going to be the highest point the sun ever gets for us. You can see that means the sun is never directly above us. The sun is always to our south. Now, if you were, say, here, then at various parts of the year, the sun would be to your south, then it would be directly above you, and then for a little bit, it would actually even be to your north. Now, for us, it's always to our south because the furthest it gets is the Tropic of Cancer. So summer solstice happens for us, that means the sun's here. And then for the rest of the year until we get to the winter solstice, it's going to venture down, it's going to pass the equator, then it's going to venture all the way, that's when we get fall, the fall solstice, or I guess equinox there, I think, if I'm using those terms correctly. You go all the way down, here's winter for us, then it goes back up to spring when it's over the equator, and then back up towards summer. It bounces back and forth. But what that means is the part of the earth that gets the most direct sunlight is going to be the equator. The sun passes directly over it twice every year. And so at the equator, it's getting a ton of light. And what that light is going to do is it's going to heat up the air. So if we go back to our slide here, I'll switch to this slide so it's a little bit bigger of an image. Here at 0 degrees, the air is getting warmed up. So the air is getting warmed up a lot. And as we saw in the smoke, warm air is going to rise. So at the equator here, warm air rises. So the rising warm air is going to go up into the atmosphere. So it's going to go straight up from the earth into the atmosphere. Now, it can't go up forever, right? Otherwise, all the air would escape. And basically what it's going to do is it's going to go up, and then when it gets to a certain point, basically when it hits like the ceiling, it's going to venture out to the sides. It's being pushed in both directions. So the air will go up, then it's going to get pushed out, and it's going to go up or down. If it goes up, it'll continue going up, and it will fall back down to the earth at right about 30 degrees. So at 30 degrees, it's going to start falling back down. Now that air is going to fall, but eventually it's going to hit the earth, and it's going to start to move out. And so at 30 degrees, it's going to impact the earth and then move back down to either the equator or up towards the poles. And then that air is going to move up. It's going to start rising again at 60 degrees, and then it's going to again hit the ceiling, move out, go either north or south, and then come back down at 90 degrees. So you can see we have these basically three cells. So these three atmospheric cells, one between 0 and 30, one between 30 and 60, and one between 60 and 90. Now what's really important is for you to understand when air is going up and when it is going down. So at 0 degrees, air goes up. At 30 degrees, air comes down. At 60 degrees, air goes up. And at 90 degrees, air comes down. That movement, vertical movement of air, is going to become very important for describing what will happen at those regions on the globe. Okay. So, due to a variety of physical things that we will talk about here in a second, when air moves up, pressure goes up. Pressure goes down. Think about when you're going up the Sierra Nevada mountains, right? Have you ever driven up to Shaver or Huntington, and the higher you go, the better the experience is. Your ears are going to want to pop, right? You're going to get pressure in your ears. And the reason why is because if you started at the valley, you're under a higher pressure than the top of the Sierras. So as you drive up, the air within your ears, within your sinuses, begins to expand because it's under more pressure than the surrounding environment, and that gives you a little bit uncomfortable feeling. And then when you adjust that by yawning, or sometimes even sneezing, or whatever it might be, or just time, it'll adjust that pressure balance to be equal to what's outside. And so, same thing if you take like a chip bag, you buy it in Fresno and drive up the mountains with it, the chip bag will slowly expand. It may even pop. And so, the pressure is lower up in the Sierra Nevadas. And part of that has to do just with the column of air that's above you. The atmosphere, the highest point of the atmosphere, is basically always the same. And so if you're lower in elevation, you have a bigger column of air above you. And as you move up elevation, that column gets smaller. Really big column, you move up elevation, column gets smaller. And so there's less pressure the higher you go. So as the air moves up, pressure goes down. But if pressure goes down, just like that chip bag, right? We took the chip bag from Fresno all the way up. Pressure goes down, then the volume expands, right? The bag expands. So as air moves up, pressure goes down, but volume goes up because there's less things holding it together. So it starts to push out. Now, because of that, the temperature also goes down. And the reason for that is that, say you have a packet of air, just some amorphous packet of air, and you allow it to expand. Well, when you first had it, it had a certain amount of energy, right? And as it expands, it has the same amount of energy, but it's now over a bigger area. So the amount of energy per area becomes less. And that means is equivalent to temperature. So temperature is mainly a measure of energy. And so temperature then will go down. So as air moves up, pressure goes down, volume goes up, and temperature goes down. And I can show you that here in the simulation. Now, this simulation is built for more complex physics classes. You don't need to know all the pieces of it, just what I'm going to explain here. And so we're going to completely ignore some of these things. We're going to be looking at adiabatic compression and adiabatic expansion. That's what we're describing and what we're talking about here. And all we care about is pressure, volume, temperature, right? And we don't care, let's ignore the units here for now, because we don't really care if it's Kelvin or kilopascals or anything like that. So right now, this little green dot is right here at a volume of 3, a pressure of 200, right? Now notice 200, 3, and 600. Now if I go up in the atmosphere, I told you that the volume will expand, right? And so we're going to go adiabatic expansion. That's the equivalent of going up in the atmosphere. So I expand it. Notice how that square gets bigger. So the pressure went from 200 to 123. The volume went from 3 to 4. So the pressure went down, the volume went up. Temperature went down. I can go back for you. So temperature at 600. Temperature is now at 495. So pressure down, volume up, temperature down. Now, if I go back, so here's where we started. And let's say you started off at shaver and went down, right? Well, if we did that, if we do adiabatic compression, pressure went up, volume went down, and temperature went up. And so if you can describe those patterns and how those move back and forth, you'll understand everything we're going to talk about here. But it does take some time to work through. You likely will not understand it from this video alone. Spend some time with it, come to office hours, watch the supplemental videos on it. Make sure you can understand that central topic there. Air moves up, pressure goes down, temperature goes up, volume goes up, temperature goes down. Air goes up, pressure down, volume up, temperature down. And then the opposite is true, right? So falling air, if air goes down, pressure goes up, volume goes down, and temperature goes up. Now, what's really important here, so here's tap water and here's cold water put inside of these little cut-off water bottles. Now, you just take 2 cut-off water bottles, pour tap water in one and pour cold water in the other, and that's the only thing that you do. If you notice on the outside of this one, there's no condensation, and on the outside of this one, there is condensation. Why is there condensation on the outside of this bottle? Think about that for a second. What caused that condensation to be there? Well, what happens actually is that there's air, or there's water in the air around us all the time, right? There's varying levels depending on the humidity and things, but there's always pretty much water in the air. And what that means is that water is existing as a vapor. It's in a gaseous state at that time. And all those water molecules kind of differ. Some of them only need a little bit of, or only barely in a gaseous state. And if you were to cool them off just slightly, they would turn into a liquid. And other ones would take a lot more energy to turn into a liquid. And so depending on how cold your air is, it's going to take some of that energy from the water vapor. And if it cools it off enough, it'll turn into a liquid. It'll go from a gas to a liquid. And the cold water here cools off the air on the outside, which means it cools some of those water molecules that are in the air, and that some of those water molecules will then turn into a liquid. So what that means is if air cools off, water will turn from a gas to a liquid. That's the key piece there. Cooling air will cause precipitation. It will cause water to enter a liquid state. So let's look at this here. So air mass goes up, pressure goes down, volume goes up, temperature goes down. Because of that, if temperature goes down, water holding capacity of the air goes down. What do I mean by that? Remember, air is holding liquid in it, right? And the amount of air it holds depends on the temperature of it. And so if the water holding capacity goes down, the amount of water that air mass can hold is less than it was before, right? And so what will happen then is if, say you had a packet of air that had a lot of water in it, and you cool it off so that way the water holding capacity goes down, some of that air, the water has to leave because the air can no longer support it. That means it's going to fall as rain. That creates precipitation. Now the opposite is true of falling air. Air mass goes down, pressure goes up, volume goes down, temperature goes up. And that will create an increased water holding capacity because the temperature is increasing. So now you have a packet of air that has some water in it, but now water capacity goes up, it can now hold more water, right? And so that can suck up water from the environment. So rising air will tend to have a lower water holding capacity or a decreasing water holding capacity, creating precipitation patterns. Falling air will have a higher water holding capacity, creating a water draw from the environment, sucking up some of that water. Okay, so now let's map that out on this map. So remember, rising air, as air rises, pressure goes down, volume goes up, temperature goes down, water holding capacity goes down. So at 0 degrees, as the air rises up, because of those patterns, water holding capacity will decrease. If it decreases, and remember the tropics are really wet, so that air mass originally was really saturated with water, that means it can no longer hold that water, and it's going to fall as rain. It's going to fall as precipitation. That's why the tropics get so much rain, because the water holding capacity is decreasing as the air mass moves up. Now, that air mass is going to move either north or south and then start coming back down at 30 degrees. Now remember, falling air, as it goes down, pressure increases, volume decreases, temperature goes up, water holding capacity goes up. And what that means is this air is going to start sucking up water from the environment, right? It's going to create a lack of precipitation. It's going to draw water from the environment. It's like a sponge pulling water out. Now, the air mass is going to move up or down again. At 60 degrees, it's going to go up. Again, air goes up, pressure goes down, volume goes up, temperature goes down, water holding capacity goes down, and that's going to create rainfall. And so we get a lot of like boreal forests in this region, right? And then at the air mass again moves north to south. Polar cells, they go down at the 90 degrees. That means pressure goes down, or pressure goes up, volume goes down, temperature goes up, water holding capacity goes up. And at the polar cells, we basically have deserts. They don't get much rain. They have a lot of ice built up over a very long time, but they don't get that much precipitation. So they don't really get that much rainfall. Now, so keep that in mind. 0 degrees, lots of precipitation. 30 degrees, it's sucking water from the environment, not precipitating. 60 degrees, more precipitation. And 0 degrees, not much precipitation. So if we go to this biome viewer that describes the different biomes on the Earth, so let it load up here. Here we go, get it to show the grid lines. Okay. So Tropic of Cancer, Tropic of Capricorn. Here we have the equator. Now, if you look at the equator, tropical forest, tropical forest, tropical forest, all the way around the Earth. That's because of that high precipitation pattern. That's because air moving up in the environment. Now, if we go to 30 degrees, which is right about here, we have the deserts of North America, deserts of Africa, deserts of the Middle East. A little bit of a change here as we get towards Asia, which is normal. There's a lot more complexity here than what we're simply describing. But you can see that most of the deserts fall at 30 degrees. Or if we go down to the south, deserts of South America, deserts of South Africa, deserts of Australia. Most of the world's deserts fall at either 30 degrees north or south. And then when we go to 60 degrees north, we have a bunch of forests, right? Forest. Because that rising air causes precipitation. There's not much down here at 60 degrees, so we're going to ignore that. So you can see as air moves up, it causes the precipitation patterns, causes tropical forests or temperate forests. As air moves down, it sucks water from the environment and creates deserts. So, due to this adiabatic cooling and expansion, we now understand or can describe where the different biomes will occur. Tropical forest, where air goes up, or temperate forest where air goes up, deserts where air comes down, right? Now, based on what we just talked about, which direction do you think the wind is going or the air is moving in Fresno? So try and recall, where was Fresno at on the map, and then which way would the air be moving? Okay, so Fresno was sitting right about 32 to 42 degrees, or that's California. Fresno sitting right about 36. Now, if you look at this atmospheric circulation pattern, that means air came down at 30 degrees and then is moving up through Fresno, right? So the air tends to be moving up in Fresno, or moving north, right? The air is moving north in our region. And that's not just Fresno, that's basically everywhere between 30 and 60. The air is moving north in a northern direction. Now, the Earth is also spinning, and so that changes a bunch of the patterns here. So this map shows that, like, basically the speed at which the Earth is spinning on different parts of the globe. And you might be asking, well, why would it spin at different speeds if it's all connected? It's because it's a sphere, right? And so the further out you are from the center of the Earth, the faster you're spinning, right? And since it's a sphere, the fastest rotation is around the equator. And as you go north or south of the equator, the speed at which you are spinning decreases, right? It's basically the equivalent. If you were just a foot off of the center of the Earth in the Arctic, right? So you found the very center of the point of rotation of the globe, and you walked out like 3 feet or something. Well, you could walk around the Earth pretty quickly, but if you stood still, then you would have to wait 24 hours for you to come back to that point, even though it might only be like 6 feet, right? You'd only be actually traveling 6 feet of distance. But if you went on the equator, the distance that you'd have to travel to walk all the way around the circle of the globe at that point is massive. You never have a chance. But you still spin around it in 24 hours. And so it doesn't matter where you're at on the globe, you will spin around it in 24 hours. It doesn't matter if you're 1 foot away from the point or millions of miles away from the point. That's obviously too far for the Earth, but the point is that you will always rotate around the Earth in 24 hours, no matter how far you are, or basically the radius you are from the center of the Earth. What that means is that at the equator, the Earth is spinning really fast. And the further you get to the poles, the slower it gets. So you can see at the poles, it's almost standing still, right? Tangential speed of 0, it's barely moving. At the equator, it's moving really fast. And as you go north or south, the speed tends to decrease, right? So what that means is that we in Fresno are moving slower than somebody that is south of us, right? So let's go back to this map. If it'll work for me. Okay, so we are sitting here. That means we are moving slower than somebody that's at 30 degrees. So the people that are down in like SoCal, right? We are moving at a slower rate than they are around the globe. So we are here. We are moving slower than they are here, right? Now, if you look at its air mass, that means the air is moving from 30 degrees up to us, right? Because air is moving north from 30 to 60. That means the air that is moving from 30 to 60 started off traveling at the speed that it was at when it first came down. So it started off traveling at the speed of the Earth at 30 degrees. Generally, it's a little bit complicated, but the atmosphere basically rotates almost at the same speed as the Earth does. What that means is that if a cloud or air mass is moving at 30 degrees, it'll spin at the same rate as the Earth does. But when it moves north, right, there's a lag period there, which basically means that if a cloud moves from 30 degrees up, it started off moving at the same rate it did at 30 degrees. But if you move north, right, the Earth is spinning slower relative to what you were at 30 degrees, and you will tend to outrun the planet, right? And so you can see this turn here. The Earth, this is the air mass moving. As air moves from 30 to 60, it'll turn away. That's because the Earth beneath it is moving slower. So it's basically outrunning the globe, right? So if it moves from here, it's moving pretty fast. And if the cloud moves up here, it's going to be moving faster than the Earth. So it's going to outrun the direction of the Earth. Now that's really interesting, and we call that the Coriolis effect. What that means is that if you move from a northern or southern direction, say in the atmosphere, right, or like a waterway or something, your apparent direction on the land will change because you are moving at a different speed than the Earth is, and that will cause some sort of a rotation. And you can see if you go from 30 to 60, you'll turn right, you'll turn east because that's the way the Earth's spinning, and you're going to outrun it. And if you go from 30 down to 0, you're going to be going slower than the Earth beneath you, and you will turn to the west, right? And so the Earth will be outpacing you. And so you can see, depending on which way you move, if you move down south, if you move in a southerly direction, you move slower than the Earth. If you move in a northerly direction, you move faster than the Earth. So here's another map of that. 30 to 0, you're going to be moving towards the west. That creates a westerly wind direction. I don't like the way these are named. These are called the westerlies. This is a western direction of the wind, though. These are winds that come from the west. So if you go from 30 to 0, the wind will move to the west, coming from the east. And same thing here, 30 to 0. So these create the trade winds, moving in a western direction around from 30 to 30 across the globe. From 30 to 60, you have winds that are moving from the west to the east. We call these the westerlies. Same thing down here from 30 to 60. And then you have the easterlies that move from the 60 degrees to the 90 degrees. So these ones are moving from the west or from the east to the west. So you can see how the global patterns of wind are starting to be shaped by these simple physical factors. Now, let's start to look at our own little region here. So here's a wind map of California. And what you can tell here, which is really interesting, so the direction, the bigger the block from these little wind sensors, is the direction the wind was coming from, not the direction it's going. So you can see most of these little wind receptors have wind or have blocks that are the largest towards the west, meaning the wind is coming from the west. It's heading east, right? So most of these blocks, you can see these here, they all have the most blocks on this side of their little orientation, meaning the wind is coming from the west. Now, if we go back to our little map here, that describes what's happening here. It's coming from this direction and blowing across. So, remember, we're talking about what the whole point here is to get a holistic perspective of what determines California's climate and environmental parameters. So we talk about the mountains, the valleys, all the little structures there. I'll open the topography map up again so you can get a reminder of it. So here's California, here's mountains all the way around us, right? All of our water, by the way, does drain out right here through the bay. So it all moves up and then out the bay. It doesn't move through these mountains. And so we have mountains to our west and mountains to our east, right? Okay. So next we're going to talk about rain shadows. So a rain shadow is basically exactly what we just described. This adiabatic process where if air moves up, the volume goes up, the pressure goes down, the temperature goes down, water holding capacity goes down. And the opposite for falling air, right? So let's say we have the Sierra Nevadas here. And here we have some clouds that are a storm that's going to be moving through. Remember, we talked about why in our region, the wind is moving from the west to the east, meaning it's moving from the Pacific Ocean over the Coast Range, through the valley, and then up the Sierra Nevadas and over into Nevada. And so Fresno would be over here, and over here would be like Bishop or something. So as the clouds move up, they will rain a lot on the western slope of the Sierra Nevadas, and then leave no rain over here. Why might that be? Well, remember, rising air. So rising air goes up, or pressure goes down, volume goes up, water holding capacity goes down. And so because of that, it rains, right? And as it goes up, it's like squeezing the sponge more and more and more and more. And so as the Sierra Nevadas are really tall, it drops pretty much all of its water. And on the east side of the Sierra Nevadas, we have a big rain shadow that covers most of Nevada and several other states. So you get no rainfall over here. That creates a rain shadow. The same thing happens on the Coast Range. It's smaller, but the same thing happens. Air moves from the Pacific Ocean up over the Coast Range, drops all of its rain on the western side of the mountains, then comes over the peak of the Coast Range and drops into the Central Valley. And when it does that, it doesn't have any more water in it. And so if you drive over to the west side of the valley, you'll see that it's much drier than it is over here. Even though we're in a really dry environment, it's much more dry on the west side of the valley. And it's all driven by pressure systems. High pressure down low and low pressure up top. Okay, so let's explore California a little bit. Okay, so here's California. Now, if we zoom in here, so here's the Coast Range Mountains. If you notice, look at all this green, and then look at all this brown. Precipitation, rain shadow, rising air, falling air. And so, what I want to point out here is look at all this dry here, right? And look at these farms on this side. Now, hold on, let me plug in my laptop. Okay, so rising air, wet, nice, really wet environment over here, lots of vegetation. Really falling air, really dry, low precipitation, rain shadow effect. As you move across, Fresno is right about at the end of the rain shadow. Then it starts to climb. The air starts to climb again. Really saturated, nice, vegetated Sierra Nevadas on the western slope. You go to the eastern slope, dry desert, right? Now, what's interesting here, though, the rain shadow for the Sierra Nevadas is massive. It's a huge rain shadow. You can see all this dryness here. Not all of it's caused by the rain shadow, but a lot of it is. While the rain shadow for the Coast Range is small. Now, why might this be important? Why is this important for a plant science class? Well, one, it describes why we get what rain we do get here, and I'll talk more about when we get the rain and why. But also, if this is a rain shadow here, it means there's not going to be that much water for the crops that are on this side of the valley. All these crops that are being planted here are being planted in a rain shadow, meaning that they're not going to get much natural water. They're going to be dependent on water from aqueducts, from dams, from other sources, right? And so if you're trying to design a way to put in crops in an area where you might get the easiest access to water, this probably wouldn't be it. Another issue with this area here is that it typically has really saline soils. So a lot of the crops on the side will deal with salinity issues in their soil. Because a lot of these plants here, let me see if I can find a spot to put this little guy down. You can look at it. You can see what the landscape is like around here. And a lot of these plants are salt adapted plants. And so they can deal with salt, but the agricultural plants that we have don't typically deal with salt very well. Okay. Now, California has what we call a Mediterranean climate. It's when we have cool, wet summers and cool, wet winters, warm, dry summers. We get pretty much all of our rain in the winter and pretty much no rain in the summer. Our winters are cold but relatively mild, and our summers are hot, often extremely hot, right? That's a Mediterranean climate. Oddly enough, and if you've been here your whole life, you might not realize it, that's unusual. That's not what most places are like. And so there's several reasons why California is like that. So we're going to look at several maps here, a wind map and a pressure map. So here's a wind map. And if you notice the wind patterns, so notice this wind's coming in and it's starting to circle here. And as you watch, if you watch one piece of one little arrow, it moves from the outside and it moves towards the center. And the same thing is kind of happening over here. And then if you look at this one over here towards Japan, you'll notice that you have one that's spiraling, but the air, rather than moving towards the center, is moving out, right? So air is moving away from the center here. And at these two, air is moving, like this one towards Hawaii, air is moving towards the center. That's caused by pressure. So there's different pressure things that are going on in the atmosphere. And I can show you this on this map. Okay, so air moving towards the center, air moving towards the center, air moving away from the center. Towards the center, away from the center. These are low pressure systems. These are high pressure systems. Now think about what happens to the wind here, right? Let's zoom in here. If all the air is spinning in a circle and it's slowly moving into the center, where does it go, right? All the air just can't keep moving to the center. It has to go somewhere. The planet is beneath it, and so it can't go down. So it means it has to go up. So if low pressure systems draw air in, and they're causing it to spiral towards the center, that means air is going to move up. And then what happens when air moves up? We get rainfall, right? So low pressure systems bring in storms. High pressure systems, on the other hand, are the opposite. They bring in usually warmth. They bring in a more stable environment, one that's not really prone to high winds or precipitation patterns. And so storm, high pressure system, that's not going to have any storm-like qualities to it. Now, what's more interesting here is if I go to our daily forecast for Fresno, let's go to 10-day. It's a Thursday right now, so we're here. Friday we're gonna start to see a little bit of rain, but then Saturday we're gonna see a bunch of rain here. So on the 13th we're gonna see a lot of rain. So let's see what that looks like here on this pressure map. So if I go to the 13th, actually let me back up. Here we are right now. Here's Fresno. It's pretty nice, 80 to something degrees outside. It'll be about 80 degrees tomorrow, right? And if you look at it, it's red. You can see the air is moving away from the direction of the center. And so we're in a little bit of a high pressure system right now. If I go to Friday, remember Friday is starting to get a chance of rain. You can see that it's turned blue. We now have a low pressure system forming. And if I go to Saturday, you can see we have this low pressure system right off of our coast. Let's see, what time does Wunderground predict rain? Right about 1 p.m., so earlier in the day. Wait, yeah, 1 p.m. So let's go to here. You can see it's blue, blue, blue. And you can see that low pressure system moves over Fresno. So that rain that we're going to get is caused by a low pressure system moving over Fresno. And so if low pressure systems hit us, we get rain. If high pressure systems are there, we don't get rain. Now, I don't know, this doesn't let you move that far in advance, so it won't let me go any further than that. So we can see high pressure systems, stable, warm environments. Low pressure systems, wet environments, right? Now, here's a map of Mediterranean climates. California, parts of Chile, parts of South Africa, parts of Australia, and the Mediterranean, which is named after. What's interesting is each one of those locations have what we call a semi-permanent high pressure system. And so you can see we have one here. They have one here in South America, Africa, Australia, and the Mediterranean. Remember, high pressure systems don't allow rain. They can block rain from it. Now, what happens here, you can see these low pressure systems out here. The low pressure systems will bring in storms. Now, if you see that you look at this high pressure system, right now it's kind of low in this image. This is January, where we would typically be seeing rain. This high pressure system is kind of like California's shield. During the summer, we have the pressure system really high up. And so it's blocking all the way up here. And so it blocks California. Any low pressures that come in tend to glance over us. And so we don't get hit by any of them. So that will start to be moving in right about now. It's in the spring. It'll start to be moving in. It's going to block all the storms from us until late fall when it starts to be lowered back down. And the low pressure system kind of falls a little bit. And when we drop that shield, low pressure systems start to come in and they will start to rain. And so we'll start to get rain in the winter. So this movement of this high pressure system over the year, up meaning summer and down meaning winter, allows us to have a Mediterranean climate. When it's up, warm and dry. When it's down, cool and wet. Right? And so the movement of this pressure system gives us this Mediterranean climate. Okay, so to recap, we talked about adiabatic warming and cooling, atmospheric circulation patterns, which are pretty complex, so make sure you study them, bioinformation related to atmospheric circulation, rain shadows, and the factors associated with creating a Mediterranean climate.